Integration is sometimes called the antiderivative. So integration is the same as the antiderivative. It's the opposite. That's the way they are linked. For instance, if you had some sort of quantity and you find the derivative of it, that would give you a rate. Now, if you've got the rate already and you find the integral, that is, you integrate the rate. If this is, you've got a function here, some function of x or function of time, and you've got a rate, and you do the integral, you're going to get a quantity. Examples, if we had distance, and then you found the derivative with respect to time. If this is distance, you will get speed. If you've got the speed and you integrate it, you'll get back to integrate, I-N-T-G-R-A-T-E, horrible writing. If you integrate speed, you'll get back to distance. Another example we've come across is another example of quantity was sort of volume. So you had so many litres in a tank, and if we find the derivative with respect to time of that, if we differentiate it, we get flow rate. So many litres per minute flowing into or out of some sort of quantity or some container. If we've already got the flow rate as a function of time and we integrate it, then we'll get the volume of water that goes in a particular time that flows out or into that thing in a particular time. So derivative gives us instantaneous rate. When we integrate rate, we go back to volume. Okay, so let's have a look at an example, and that might help explain. There's a whole table of integrals, just like there's a table of derivatives you need to know, but we'll just use an example to introduce it. Say a car is travelling such that its speed is given by v of t, and that's equal to 25 minus t squared, where the velocity or the speed in meters per second and times in second. Okay, so this is its velocity. Well, velocity and speed for our purposes right now, we'll use the same terms. You'll learn later on that velocity has another component to it, direction, but we're not going to worry about that for the time being, so we'll interuse speed and velocity for this example. So its speed is given by 25 minus t squared, where t is in seconds. Okay, so what we've asked to do, how far does it travel? And so t, let's go back to the domain for t, is 0 less than or equal to t less than or equal to 5. So in other words, it's slowing down. How far does it travel before it stops? Okay, so we've got, let's look at a graph. we've got 1, 2, 3, 4, 5. So this is time, and this is my speed. 5, 10, 15, 20, 25 is up here. So that's 5, 10, 15, 20, 25. So when t is equal to 0, it is travelling at 25 metres per second. So that's way up there. 1, 2, 3, 4, 5 seconds. So when t is equal to 1, 1 squared is 1, so it's going at 24 metres per second. So that's 124, the coordinate. At t equals 2, 2 2s are 4, and 25, 21. At t equals 3, 9, t squared 9 from 25 is 16. T equals 4, 16 from 25 is 9. Oops, we've forgotten, we're going to jump over here. So that's 316. The next one across will be 4, 9. And the lucky last one, it's 5. It's come to a stop down here. So that's 5, 0. So you can see that it's a parabola. You knew that already because it's 25 minus t squared is a parabola. Not a straight line. And we've got to calculate the distance it's travelled. Okay, well, how could we do that? Because this is a curve. We could actually just say, right, if it travelled at 25 meters per second for the full 5 seconds, we could say that distance travelled, you know that distance equals speed multiplied by time. So if we assume that it travelled at 25 metres per second for the full 5 seconds, which it certainly didn't, it would have travelled 25 times 5, 25 metres per second. So at 25 metres per second for the full 5 seconds, it would be 25 times 5, which is equal to 125 metres. Now that's grossly inaccurate. It's the same as saying it's the area of this big rectangle here. So it goes up 25 and across 5. You can see that that's not going to be correct because it's slowing down. After 1 second, it's only going 24 metres per second. After 2 seconds, it's only going 21. After 3 seconds, it's only going 16 and so on. So it's slowing down. So there's nowhere near 125 metres is going to be covered in the full 5 seconds. So another approach might be to say, all right, let's just split it up into 5, each of the 5 seconds. And we calculate the distance travelled in each of those 5 seconds. And one way to do that is to actually assume that it's going to travel for the full 25 metres a second, just for that 1 second. So if we look at, so 5 rectangles, so the distance, this is another attempt. So these are called strips. So we'll go 5 strips. 1, 2, 3, 4, 5, each of these strips going up. And we're going to calculate assuming it went for 25 for that, so it'll be 25 times 1 will be the distance travelled in that 1 second. This will be 24 times 1. And this will be 21 times 1. Plus 16 times 1 for this one here. and then 9 times 1. And if you add all those up, I think we get 95 metres. So it's come down significantly. Because we're going above the actual curve, the curve, maybe if I do it in another colour, it might sort of stand out a bit more. Okay, so the curve's in green. Because we're working out the rectangles above the curve, these are called upper rectangles. And we get 95. You know that it's not going to travel that distance because we've calculated, say, between 3 and 4 seconds, we've calculated this bit up here, which it won't have travelled. It'll only have travelled below there. So it's not going to actually calculate. We're going to be way too generous here. So we've just used time, 1 second, times speed. We still use speed multiplied by time, but we've gone for the speed at the very start of each second. What we could equally do is do the speed at the end of each. So we'll do this rectangle here, find the area of that. So that's my time, 1 second, and this is the speed, 24. So using lower rectangles, and this is using 5 strips. We've got 24 times 1, so that's the distance, the travel we think it is an approximation in the first second, plus 21 times 1, plus 16 times 1, plus 9 times 1, plus 0 times 1. So 0 is the speed at the end of the fifth, and times 1. So we were saying it's not going to travel any distance in that last. And you add those up, and we get 70 metres. Now, once again, that's going to be way under what's actually going to happen. We've actually done all these lower rectangles. This one doesn't even get a Guernsey here. So once again, it's going to be somewhere in between. Now, if we draw a straight line between that point and that point, those straight lines are going to be fairly close to the curve. Not quite on it, because the curve obviously has got a bend in it, and these straight lines. So if we could find the average of these two, so the average of the upper and lower, and find the average of two numbers, we simply add the two numbers and divide by 2, and with that we get 82.5 metres. Now that's an approximation as to how far we've actually had this car travelling. 82.5 metres is an approximation, and that's using just 5, splitting this up into 5 steps. You could see that if and it's a marked improvement with one strip. We just did the 25 times 5 and found the area of that rectangle, got 125. We've come down to 82.5, which is going to be fairly close. The more strips, the better. And integration. Now, what you're doing with integration is you are summing. Integration is the sum, with sum you add up, of an infinite number of rectangles. The area so integration is a sum of the area of an infinite number of rectangles over a particular domain. So we add up an infinite number the area of an infinite number of rectangles. So if I made them, these are 1 second, a tenth of a second, you're going to have 50 rectangles. Well, integration's even better than that. It does an infinite number of rectangles. Now, because it's the sum of the areas of these, we use that symbol. It's like an elongated S for sum, and that's the integral sign. So what we're going to do is we're going to integrate our function. Now, our function is 25 minus t squared. So we're integrating that. We're going to do it with respect to time. So dt, just like we did dv dt, or ds dt or dy dx, we're going to integrate with respect to time. And we're going to do it between 0 and 5 seconds. So these are the values of t that we're interested in, between 0 and 5. If we wanted to find the distance that travel between 2 and 4, we'd go from 2 to 4. And that would calculate the area under the curve, which would be the distance it has travelled. All right. This will give us the exact distance. Now, there is a table of integrals, but for the time being, I'm just going to give you what the rule is. We integrate 25, and that is 25t. Because if you find, we said that the integral is the opposite of derivative. So if we find the derivative of this, we should get 25. The derivative of 25t, d dt of 25t is 25. Minus, now the integral of t squared, I'm just going to give it to you right now, but I'll explain this a little bit in later videos. T cubed on 3, because you find the derivative of t cubed on 3, you get 3t squared over 3. The 3's will cancel and you get t squared. Don't worry if you don't understand that for the time being, but that is the integral of t squared. Now, we put square brackets, and we're interested from 0 to 5, because we want the distance it travelled between 0 and 5 seconds. The process is to substitute that in the brackets first. So we put the top one in, so that'll be 25 times 5 minus 5 cubed on 3. Always minus, I'll explain this later as well, put the 0 in there. So 25 times 0 minus 0 cubed on 3. That's equal to 125 minus 125 on 3 is 41 2/3. So that's that bracket done, minus, that's 0 minus 0, well that's all 0 there. 125 minus that will be 83 1/3 meters. Okay, so that's the exact distance that, using integral, that is the exact distance. How does it compare with our rectangles we did, our average of the upper and lower? Well, we got an answer of 82.5. The actual answer is 83 1/3. So that's probably not a bad approximation. If we did 10, we might even get closer to 83 1/3. So that's just an introduction as to what integration is all about. If you integrate, this was a rate. The rate was actually the speed that it was traveling at. If we integrate rate, we get a distance. And we integrate speed, we get a distance. If we integrate flow rate, we will get quantity. It could be litres or megalitres, depending on what the flow rate was. And integration is the opposite of differentiation, and it is an adding up of the area of an infinite number of rectangles. So this gives us the area under the curve between the curve and the x-axis. So that shaded area is exactly the same as that integral. We should have that going out there. So that's an important idea to get your head around, that the integral between 0 and 5 would be the area under the curve, and it just happens because we've got time and speed. Times multiplied by speed is going to give us distances, which is what we did here. Oh. All right, so that's an introduction to integral. We're going to come back and do some more examples.